All right, welcome to another deep dive. Today, we're getting into some seriously fundamental stuff in machine learning, the real nuts and bolts of how AI figures things out. Specifically, we're going to unpack this idea of linear classifiers and this whole concept of separating data with, well, a line, basically, or a hyperplane when things get a bit fancier. And of course, we got to talk about margins, that little safety zone that helps our classifiers be a bit more
Yeah,
robust.
exactly. We've got to have that margin.
Then we'll dive into the perceptron learning algorithm, how it learns to draw these lines and the conditions that guarantee it'll actually find a solution. And then we'll move on to logistic regression. This one's really cool because it gives us probabilities instead of just like a yes or no answer. Much more nuanced, much more real world.
Totally. And for this deep dive, we're pulling mainly from our trusty ML theory notes, specifically from week 9 and then the early parts of week 10, 11, and 12. So if you're following along, that's where we're at. The mission here really is to give you a really solid intuitive grasp of these core classification techniques, or those moments where it all just clicks, without getting bogged down in the math too much.
Hopefully, exactly. We'll highlight the aha moments.
Uh-huh.
Okay, so first things first, let's unpack these linear classifiers. What are we even talking about here?
Sure. So at their heart, linear classifiers are making decisions based on a relatively simple calculation. You've got your data points, each with its features, and the classifier is using a weight vector, kind of like a set of knobs or dials almost, to combine these features. The classification rule, as we see in our notes, is hx equals sine Wescas.
Yeah.
If this calculation spits out a positive value, boom, one class. Negative other class, typically we represent those as 1 and -1.
+1, -1, yeah.
Yeah.
So essentially, we're drawing a line, right, to separate our data into these different categories.
You got it. And in higher dimensions, more features,
Yeah.
it becomes a hyperplane. But it's the same idea.
Yeah.
And this weight vector, W, it's the one that's determining like the orientation, the location of this decision boundary.
This separating line.
Exactly. Now, a big challenge, right, in machine learning is minimizing errors. We want our models to be as accurate as possible. Ideally, we'd love to just minimize this thing called the 0-1 loss, which basically means counting up all the misclassified points, how many did we get wrong. The problem is directly minimizing this error count. It gets really tough computationally, especially with big data sets. Computer scientists call this NP hard, meaning the time to find the absolute best solution explodes as you get more data. Like it could take forever.
Okay, so we can't just brute force count all the errors and find the best solution. It's too computationally expensive.
Exactly. That's why we need these smart workarounds, like the perceptrons update rule, right, or the probabilistic approach we see in logistic regression. They go after more manageable objectives.
Okay, so directly minimizing those mistakes, not so easy. So then we bump into this idea of linear separability. What's that all about?
Well, a data set, we call it linearly separable. If we can actually find like at least one weight vector that just slices perfectly through the data, separating everything. Mathematically, what that means is for every data point, the product of weights, and the true label is greater than or equal to 0. Think of it like this. We can draw that line, have all the positives on one side, all the negatives on the other. No one's on the wrong side of the tracks, so to speak.
Perfectly divided, clean cut. I like it.
Right. But sometimes, as our material mentions, a data set might just barely be linearly separable. Like imagine some points huddled super close to that line.
Oh, yeah, right on the edge. So it works, but it's maybe not ideal.
Exactly. It could be a little fragile, especially when you're dealing with real-world messy data.
So that's where I'm guessing linear separability with a margin comes in to give us a little breathing room.
Right on. This is like a stronger requirement. It's not just about separating. It's about separating with some clear space. That condition becomes Weichi. That's our margin, a positive value. Imagine it like the width of a street between our two classes.
Okay, so wider street, more comfortable, less chance of those edge cases messing things up.
Yeah, exactly. It's all about robustness, right? You have a wider margin. Your classifier is likely to do better on new data it hasn't seen before. Less sensitive to the noise in the training data.
Yeah.
More generalizable, we might say.
Okay, I'm with you. So we've got this idea of separating the data, hopefully with a nice, healthy margin. But how do we actually find that line, that separating hyperplane in the first place? That's where the perceptron learning algorithm steps in, right?
Exactly. It's a classic, a real OG algorithm for learning a linear classifier. And the prediction rule is so simple, right? If Wanks is greater than or equal to 0, okay, we're predicting one class, let's say +1, and if it's less than 0, the other, -1.
Nice and straightforward.
Right. So we start with a weight vector of all zeros. Basically, no bias, no preconceived notions. Then we go through our data point by point. And if we hit a point that's misclassified, meaning the sign of wanks doesn't match the true label yo, we adjust our weight vector. The rule is super simple. W kills plus soup. And we just keep doing this, looping through the data until we make a whole pass without any mistakes.
So it's like every time it messes up, it tweaks those knobs, those weights, in a way that'll hopefully make it classify that point correctly next time around.
Yeah, it's like trial and error, like it's learning from its mistakes. And our notes highlight this really cool point. The number of times we update those weights, it's exactly equal to the total number of mistakes it made while learning. Pretty neat, right?
So number of corrections equals number of mistakes. Got it.
And here's the kicker. When you have data that's linearly separable with a margin, that positive margin, the perceptron is guaranteed to converge, meaning it'll find a separating hyperplane. Eventually. This is big, like a foundational theorem in learning theory.
That's huge, a guarantee.
Right. The proof, it's laid out in our material, and it hinges on these two ideas. First, we assume there's a linear separator with a margin Hank, and we also normalize the optimal weight vector W. So it has a length of 1.
Okay, so normalizing the weight vector, what's that doing for us?
Well, think of it like setting a standard unit. It simplifies the math without changing the direction of that optimal separator. It just makes things cleaner. And the second idea is this radius bound, R. All our data points, they live within this sphere of radius R around the origin, like how spread out the data is.
Okay, so we're assuming the data can be separated, and we've defined how spread out it is.
Right. Now back to the proof. First, we look at how the size of our weight vector data changes as the perceptron is learning. After T updates, our notes show the squared length of W. It's bounded, always less than or equal to TR. So It's not just growing out of control.
It's constrained. Okay. Makes sense. What else?
Right. Then we look at the relationship between our current weight vector, W rho, and that optimal one we normalized, W, their dot product. Well, this tells us how much they're aligned, right? And it's lower bounded by tau. So with each correction, we're getting a bit closer to that optimal direction.
Okay, so each update nudges us in the right direction, towards that perfectly separating line.
Exactly. Now we pull it all together with the Cauchy-Schwarz inequality. This is a mathematical tool that relates the dot product and lengths of vectors. And boom, we get a crucial result. The total number of updates, T, is less than or equal to. This is the radius margin bound.
The radius margin bound. Okay, so we finally got there. What's so special about it?
What it tells us is that the number of mistakes the perceptron makes, it's a finite number. It's directly linked to how spread out our data is, that radius R, and how clear the separation is, the margin I. More spread out data or a smaller margin, yeah, it might take more updates, but the algorithm will still find a solution. As long as the data is linearly separable with a margin, we're good. It's going to stop eventually.
It's going to converge. We have that guarantee. And it all boils down to this relationship between the data spread and how clearly it can be separated. I love how this proof makes that so explicit.
Right. The real magic, though, is not just that it stops. It's that it shows us that with enough data and a clear separation, even a simple algorithm can reliably learn. This is really foundational to understanding what's learnable, what problems we can tackle with these algorithms. It gives us confidence.
Totally. And speaking of seeing it in action, our notes even have this step-by-step example with actual data points and everything. It shows how the weight vector gets adjusted with each mistake, and then boom, convergence, it finds that separating line. Really helps visualize the whole process.
Right, and you can see the impact of the margin too. When that margin gets smaller, the two classes are closer, less distinct, the perceptron often needs more updates to converge.
Makes sense. The less clear the separation, the harder it is for the algorithm to figure out the boundary. Like, if I asked you to separate a bowl of Skittles by color, that's easy. But if it's a bowl of, subtly different shades of blue M&Ms, that's going to take you a lot longer. And you might make more mistakes along the way.
Perfect analogy. Love it. Okay, so the perceptron is great when our data plays nice, when it's linearly separable, especially with a good margin. But what if it's not so clean? What if our data is a bit more, rebellious, doesn't like to follow the rules?
It's out in the real world, being all messy and unpredictable. Then what? That's where logistic regression comes in, right? Our more flexible friend.
Exactly. Logistic regression, it chills out a bit on that strict separability requirement. Instead of just spitting out a +1 or -1, a hard classification, it gives us probabilities. It estimates the conditional probability of the label Y given the input X, or PYX. So it's telling us, hey, this data point, there's a this much chance it belongs to this class.
So it's giving us degrees of certainty. It's saying, I'm pretty sure this is a cat, or, I'm kind of on the fence about whether this is a muffin or a chihuahua. It's embracing that ambiguity that we see so often in the real world.
Right. It's not so black and white anymore. And the magic behind this probabilistic output, it's this thing called the sigmoid function. ZOO, 1 plus EO. This is where the fun begins.
The sigmoid function. Okay, I've heard of this. It's that S-shaped curve, right? Tell me more about what it does. Why is it so important?
It's a beautiful function. What the sigmoid does is it takes any real number, right, any input, and it squishes it, transforms it into a value between 0 and 1. That's our probability. So as that input, ZOO gets large positive, the sigmoid gets closer and closer to 1. And when ZOO goes negative, really negative, the output, it heads towards 0. And right in the middle, when Z is 0, the sigmoid gives us 0.5. It's all smooth, no sharp jumps, unlike that on-off switch we saw in the perceptron.
Okay, so it's taking our calculation, our WAMAX, and converting it into a probability score.
Precisely. And our notes highlight some of the sigmoid's cool properties, like its symmetry around 0.5 and the formula for its derivative. That derivative part will be important when we talk about learning the weights.
Right, how it actually figures out the best values for those weights. Okay, so we've got this sigmoid turning numbers into probabilities. So in logistic regression, the probability of, let's say, a data point belonging to the positive class, Py equals 1x, it's modeled as the sigmoid of that linear combination of features, yx.
Right. You got it.
Yep.
So we get this probability score between 0 and 1. And to actually make a decision, put a label on it, we might use a threshold, like, okay, 0.5. Above 0.5, it's one class, below the other.
Makes sense. Okay, but now how do we actually train this model? How do we find those perfect weights, the ones that give us the most accurate probabilities?
Well, we use this technique called maximum likelihood estimation, or MLE for short. The idea is to find the values for the model's parameters, the weights that make the data we've seen, the training data, as likely as possible.
So we're saying, hey, model, given this data, what weights would make this the most probable outcome? We're trying to find the weights that best explain the data we already have.
Exactly. We want our model to be like, yeah, this data makes perfect sense given my weights. And to make the math a bit easier, we often work with the logarithm of the likelihood. That's the log likelihood. Our sources show how to derive this for binary classification, starting with labels 0, 1, then adapting it for -1. 1.
Okay, log likelihood. And this is where we get the cross-entropy loss, right?
You got it. The negative of this log likelihood, that's our cross-entropy loss, a big deal in machine learning.
Cross-entropy loss. So it's basically a measure of how well our model's predictions match the real labels.
Right. And what's great is that the log likelihood, or the cross-entropy loss, it gives us this smooth, differentiable function that we can optimize. And that means we can use calculus, gradients to find those best weights.
Calculus to the rescue. I knew it would come in handy eventually.
Always does. So we need to calculate the gradient of the log likelihood with respect to the weights. How does the log likelihood change as we tweak the weights? Our notes have a nice step-by-step derivation, and the resulting formula is AC. And this has a really cool interpretation. That term, that's the error. The difference between the true label and the probability our model predicted.
So it's telling us how far off our prediction was for each data point.
Exactly. And the gradient, it points us in the right direction. Tells us how to adjust the weights to make that error smaller. And to actually find the best weights, we use an algorithm called gradient ascent, since we're maximizing the log likelihood. Yeah. So we iteratively update the weights, W0 by E20 by 820 by 900 by 820 by 820 by 820 by 89 years. That's 8 say plus 8 sweet eons. That's our learning rate. It controls how big our steps are.
So it's like we're climbing a hill, trying to reach the peak where the log likelihood is highest, and the gradient tells us which way to go, and the learning rate is like how big our steps are.
You got it. So unlike the perceptron, logistic regression uses this more refined gradient-based approach. It can handle messier data sets that aren't perfectly separable, and it gives us probabilities, reflecting the uncertainty in our predictions.
Much more nuanced. I like it. And as we're wrapping up, it's amazing to see how these fundamental concepts connect to more advanced stuff that we'll be diving into later. Like our notes mentioned the margin. It comes up again in a big way when we talk about support vector machines, or SVMs.
Oh yeah, SVMs. They're all about maximizing that margin. We'll be exploring that based on week 10 material. Finding that optimal hyperplane that gives us the biggest possible separation between classes, building on what we've learned today.
Right. And logistic regression, with its probabilistic framework and loss functions, those ideas set the stage for understanding more advanced models, like neural networks and different types of loss functions we use in more complex situations.
Exactly. And this is all covered in week 12. We'll see how the limitations of these linear models, they naturally lead us to more complex architectures like neural networks. Neural networks can learn these crazy nonlinear decision boundaries,
Right.
fitting all sorts of patterns that a simple line just can't capture. But we're getting ahead of ourselves.
Right, gotta crawl before we can walk, walk before we can run. Okay, so let's recap what we covered in this deep dive. We started by talking about linear classifiers, these models that try to separate data using lines or hyperplanes, and the importance of having a margin for robustness. Then we dove into the perceptron learning algorithm, saw how it learns from its mistakes, and learned about this awesome guarantee that it'll converge for linearly separable data with a positive margin. Then we shifted gears to logistic regression, which gives us probabilities using the sigmoid function, and saw how it's trained using maximum likelihood estimation and gradient ascent.
And we talked about the importance of the margin and the concept of loss functions. Those are key ideas in machine learning. Hopefully, there were some aha moments along the way, like understanding why the perceptron converges or grasping that probabilistic view that logistic regression gives us.
Right, the aha moments. Those are the best. Now, you might be thinking, okay, but real-world data is rarely perfect. It's not always so neatly separable. And that's a great question. It leads to more advanced topics like soft margins and SVMs, where we allow for some misclassifications, or the fact that logistic regression can still give us useful probability estimates even when perfect separation isn't possible.
And of course, you might be wondering about the limitations of these linear models, and that's where neural networks step in, right? Learning those nonlinear boundaries to fit more complex data. We'll definitely explore these in future deep dives. But for now, think about this. How often, in the real world, is data perfectly clean and separable? Recognizing the challenges these fundamental algorithms face, with all the messiness of real data, that's what sets the stage for appreciating all the amazing advancements in machine learning that have come since.
Totally. We're building on these foundational ideas, and it's only getting more interesting from here. Thanks for joining us on this deep dive.
It's been fun.